In this video, we're going to look at our second example of spinors in physics, which involves the Stern-Gerlach experiment and how it reveals the existence of quantum spin states. We're going to find that the mathematics used to describe quantum spin states is the exact same as the mathematics used to describe the polarizations of classical light waves that we saw in the last two videos. They are both described by 2x1 complex columns called spinors that can be rotated with SU2 matrices. And there is an angle doubling relationship between physical space and the quantum state space. Just like how we saw there was an angle doubling relationship between polarization space and physical space in the last video. Before getting to the spinor mathematics, let's describe the Stern-Gerlach experiment, which was performed in 1922. I'm going to call it the SG experiment for short. The SG experiment involves a beam of neutral atoms and an inhomogeneous magnetic field. A homogeneous magnetic field would have the same strength everywhere, but this strangely shaped magnetic device is able to generate an inhomogeneous magnetic field, which is stronger at this pointed tip labeled south, and weaker on the lower half labeled north. The beam of neutral atoms in the original experiment was made of silver atoms. Neutral atoms have an equal number of protons and electrons, so there is no net charge. Naively, you'd expect neutral atoms to be completely unaffected by a magnetic field. But the Bohr model of the atom that was developed in the early 1900s predicted that electrons orbited around the nucleus, and this small loop of electric current would behave like a magnetic dipole, or a tiny bar magnet. Now, if we were to send a bunch of tiny classical bar magnets through this inhomogeneous magnetic field, then the bar magnets with north pointing up would be deflected upward, since the magnetic field is stronger at this tip. And magnets with north pointing down would be deflected downward. And every other orientation of bar magnet would be deflected somewhere in between, depending on their orientation. However, after performing the experiment, this is not what we see. We only see two types of deflection, either completely up or completely down, and nothing in between. This experiment shows us that, when we measure the angular momentum of a silver atom, there are only two possible discrete results, and so the angular momentum of silver atoms is quantized. In later years, this magnet-like behavior of silver atoms was found to be not due to the electron's orbital angular momentum around the nucleus. It was later discovered that the Bohr model was wrong, and that electron orbitals come in various shapes. The first 46 electrons in a silver atom have no net orbital angular momentum overall. The final 47th electron exists in the spherical 5s orbital, which also has no net orbital angular momentum. So electron orbitals do not generate a magnetic field here. Instead, the magnetic dipole in silver atoms is due to the 47th electron's internal angular momentum, also called spin angular momentum. This internal angular momentum is sometimes envisioned as being due to the electron spinning on an axis, like a ball. However, in reality, electrons are described by wave functions, and are not tiny spinning balls, so this explanation also fails to explain the magnetic dipole. The concept of an electron having internal angular momentum has a reputation for being very difficult to understand. However, there's an analogy with light that can help our understanding here. Matter particles have orbital angular momentum when they actually curve around in space, and light rays can also have orbital angular momentum when they curve around in space. But from our last video, we know that light waves can be polarized, which allows for an internal type of angular momentum that is internal to the light beam itself. Modern quantum field theory tells us that matter particles can also have something similar to a polarization, which gives them internal angular momentum that's internal to the particle's field, instead of being due to curved paths in physical space. But we're not going to focus on quantum fields for now. For this video, we just want a basic experimental understanding of the quantized spin angular momentum of electrons. We'll get this understanding by sending a beam of atoms through multiple SG experiments. To start, let's review some of the notation and mathematics used in quantum mechanics. In classical mechanics, when we talk about the state of a particle, we're referring to the particle's position and momentum, and how these quantities change over time. But in quantum mechanics, a particle's state is instead represented by an abstract state vector, which, loosely speaking, is the same thing as the particle's wave function. Everything that we can possibly know about a particle, like its position, momentum, and energy, can be derived from the particle's state vector. This idea of an abstract state vector can be a bit confusing, but hopefully it will become more clear as the video goes on. The standard way of writing a vector in physics is to write a little arrow above the variable, but in quantum mechanics we use the Ket vector notation and write vectors like this, with an angle bracket pointing to the right. We can write Ket vectors as linear combinations of basis vectors as we normally do, or write the components of the vector in a column like this. For vectors with real components, we can get the squared length of a vector v by writing v transpose v. But in quantum mechanics, vector components can be complex numbers, so we get the squared length of a vector by doing v transpose conjugate times v. This extra complex conjugate ensures our final result for the magnitude is real. The transpose complex conjugate is called the Hermitian conjugate of a vector, and this is written with a dagger symbol. In quantum mechanics, we write the Hermitian conjugate of Ket vectors like this, with an angle bracket that's pointing left. These are called Bra vectors. You can loosely think of Ket vectors as columns and loosely think of Bra vectors as rows. When multiplied together, they give a single number. This is called their inner product. Now, one of the strange concepts in quantum mechanics is the idea of wave function collapse. This is the idea that a particle can be in a superposition of several states, but as soon as we measure the particle, it will collapse into a single state according to some probabilistic rules. Mathematically, quantum superpositions are represented by linear combinations, where each basis vector represents one of the possible states the system can collapse to. The coefficients in the linear combination are called probability amplitudes, and they are related to the probability of measuring each state after the collapse. In the SG experiment, there are only two states the particle can collapse to: either spin up, denoted with an up arrow ket, or spin down, denoted with a down arrow ket. The rules for determining the probabilities for collapsing into a given state are given by Born's rule. In simplified form, Born's rule tells us that when we want to know the probability of some state A collapsing onto a state B after a measurement, this probability equals the squared magnitude of the inner products of the states A and B, written in Bra-Ket notation like this. This inner product is sort of like the overlap between the two state vectors A and B, if we were to cast A's shadow onto B. The process of casting B's shadow onto A gives us the same result, except complex conjugated. However, since the probabilities we measure are the squared lengths of these inner product overlaps, it doesn't matter which direction we measure the overlaps in. So the squared magnitude of these two inner products are equal. Now, let's use Born's rule to try and understand the quantum states in the SG experiment better. We'll do this by putting particles through multiple SG experiments in a row. To simplify the diagrams a bit, I'm going to replace these magnets by a box with the letter Z on it. This indicates the inhomogeneous magnetic field points in the Z direction. I'm also going to rewrite the spin up and spin down states as plus Z and minus Z, indicating the coordinate directions that the particles are deflected in. Let's say that the particles in the initial beam are in some state psi. After going through the SG apparatus, they collapse into one of two states, either spin up or spin down. Now let's take these spin up particles and put them through another SG apparatus. We find that all the particles are deflected up, and none are deflected down. So according to Born's rule, the probability of measuring spin up, given a spin up state, is 1. And the probability of measuring spin down, given a spin up state, is 0. Now let's put an SG apparatus after the down states. As you might expect, all the particles are deflected down. So Born's rule tells us the probability of measuring spin down from spin down is 1, and the probability of measuring spin up from spin down is 0. All of these inner product relationships from Born's rule give us some useful information about the spin up and spin down state vectors. For example, it tells us that the spin up state has a magnitude of 1, and the spin down state also has a magnitude of 1. Also, the spin up and spin down states are orthogonal, since their inner product is 0. So in physical space, up and down are separated by a turn of 180 degrees. But in our quantum state space, where the particle spin states live, the spin up and spin down states are orthogonal, so they are 90 degrees apart. So we're already starting to see that there's an angle doubling relationship between physical space and the quantum state space. Next, we'll try the exact same setup, except rotating the SG apparatuses by 90 degrees, so that the magnetic fields are oriented in the direction of the x-axis, so that particle beams are split into the plus x and minus x directions. Performing the exact same experiments as above, we get Born rule formulas for the plus x state and the minus x state. These inner product formulas tell us that the plus x and minus x states have magnitudes of 1, and the plus x and minus x states are orthogonal. Now let's try something more interesting. Let's arrange the first SG apparatus so that it points in the x direction, and then send the plus x particle beam through a second SG apparatus pointing in the z direction. We find that the plus x particle beam is split evenly in the plus z and minus z directions. Taking Born's rule again, the probability of measuring plus z from plus x is 1/2, and the probability of measuring minus z from plus x is also 1/2. If we repeat the experiment, but starting with the minus x beam instead, we also find a 50-50 split between the plus z and minus z states. So the plus x and minus x states can each collapse into the plus z or minus z states when a magnetic field in the z direction is applied. This is telling us that the plus x state can be written as a quantum superposition of the plus z and minus z states, with the proper coefficients, because it can collapse into either one after a measurement. And remember, quantum superposition is just a fancy way of saying linear combination. In order to get the expected probabilities of 1/2 from the experiment, we need to set the coefficients for plus x to be 1 over the square root of 2 and 1 over the square root of 2. you can check that applying a plus z Bra vector to a plus z Ket vector and then squaring the result gives us the expected probability of 1/2. The same goes for applying the negative z state to the plus x state. The minus x state uses the coefficients plus 1 over the square root of 2 and minus 1 over the square root of 2. This also reproduces the expected probabilities of 1/2. And importantly, this choice of coefficients makes the plus x and minus x states orthogonal, with an inner product of 0, and also makes each have a magnitude of 1, as expected. Looking at our quantum spin space, the plus x and minus x states look like this. This continues with the expected angle doubling relationship with physical space, where a 45-degree turn in quantum spin space is a 90-degree turn in physical space. Next, let's look at a pair of SG experiments pointing along the y-axis. Looking at the Born rules, we see that the plus y and minus y states have magnitudes of 1 and are orthogonal. If we start with a y-aligned SG apparatus and then feed the plus y particle beam into a z-aligned SG apparatus, we once again find a 50-50 split between the plus z and minus z states. The same occurs if we begin with the minus y particle beam. So the plus y and minus y states can be written as quantum superpositions of plus z and minus z, because they can collapse into either one. But if we want to write the y states as quantum superpositions of the plus z and minus z states, we run into a problem. We've already used the coefficients of plus 1 over the square root of 2 and minus 1 over the square root of 2 for our spin plus x and minus x states, and we can't reuse those coefficients. So what coefficients can we pick that will still give us probabilities of 50%? The secret is to start using complex numbers. We'll write the plus y state as a superposition of plus z and minus z using the coefficients 1 over the square root of 2 and I over the square root of 2. If we calculate the inner product of the plus z and plus y states, and then find the squared magnitude, we get the expected probability of 1/2. The same thing happens for the inner product of the minus z and plus y states. The imaginary I goes away when we take the squared amplitude. For the minus y state, we use coefficients of 1 over the square root of 2 and minus I over the square root of 2. This gives the expected probabilities of 1/2. This also ensures that the plus y and minus y states are orthogonal, with an inner product of 0, and also ensures their magnitudes are 1. As an exercise, you can check that the inner product of one of the x states with one of the y states always gives a squared magnitude of 1/2. And you can also think about what this means in terms of the results of the corresponding SG experiments. So if we look at all the quantum superposition formulas we've written so far, these relationships exactly match the formulas for the Jones vectors we saw in the previous 2 videos. We can flip back and forth between them using this dictionary. It also turns out that we can arrange these 6 quantum states on a sphere like this, aligning them with the directions in physical space that they actually represent. This sphere is called the Bloch sphere. This is mathematically equivalent to the Poincaré sphere we saw in the last video, where the 6 main polarizations of light are also arranged on a sphere. With light wave polarizations, we could mix the polarizations together in various ways to get any polarization on this sphere, including elliptical polarizations. Similarly, we can mix the quantum states in various superpositions to give any state on this sphere. These correspond to states associated with SG experiments, that are aligned at arbitrary directions in space. We showed in the last video that we could rotate vectors across these spheres using 2x2 unitary matrices, written as U2 for short. Remember, rotating a vector psi with a matrix U means that its squared magnitude won't change. So the squared magnitude formula should be equal before and after the rotation. We can show that these matrices must have the property that U inverse equals U dagger, which is the definition of a unitary matrix. Now, it turns out that for rotating these quantum states on the sphere, U2 matrices are too general, because we've missed an important fact about Born's rule. As we already know, Born's rule tells us that the probability of measuring a state A collapsing into a state B is the squared magnitude of the inner product of A and B. Now, let's modify the state A by giving it a complex phase factor e to the I theta. If we now calculate the probability of our new A state collapsing into state B, we get the squared magnitude of this inner product. The phase e to the I theta gets a negative sign due to the required Hermitian conjugate. Since e to the I theta is just a scalar number, we can pull it outside of the inner product. And here, the magnitude of a product is the same thing as the product of the magnitudes. And the magnitude of a complex phase, e to the I theta, is just 1, because it lives on the complex unit circle. So the probability formula we get is unchanged compared to before. So we know that when we measure the state A, it can collapse into various other states according to some known probabilities. And we just learned that when we measure the state A multiplied by a phase factor, it can collapse into the exact same set of states with the exact same probabilities. Because the states A and A times phase collapse into the exact same states with the exact same probabilities, practically speaking, there is no difference between them. In real quantum mechanics experiments, all we can do is perform experiments over and over again and keep score of the results we get. If one scientist did experiments with state A, and another scientist did experiments with state A times phase, they would find all the statistics of their experimental results are the exact same. So physically speaking, state A and state A times phase are actually the same physical state. Even if the vectors look different, the two vectors give the exact same physics. So in quantum mechanics, a physical state is unchanged when we multiply its vector by an overall phase, such as I, -1, or any other complex phase. Now recall we said that U2 matrices will perform rotations on our Bloch sphere of states. But since overall phases don't matter, there are multiple U2 matrices that can rotate us to the same output state, each matrix with a different overall phase. So there is some redundancy in the group of U2 matrices. In order to pick a unique U2 matrix for doing rotations on our Bloch sphere, we pick the specific U2 matrix whose determinant is 1. Remember, we can always set the determinant of a U2 matrix to +1 by multiplying it by the correct complex phase. This restricts us to SU2, the group of 2x2 unitary matrices with determinants of +1. So, in conclusion, the behavior of quantum spin states is mathematically equivalent to the behavior of Jones vectors and light polarizations. Both are represented by two-component complex columns, which can be represented geometrically on a sphere. We can rotate between points on the sphere using SU2 matrices, since both quantum states and light polarizations don't care about overall phase factors, which includes not caring about overall negative signs. In the case of physical space for wave polarizations, and the quantum state space for quantum spin states, these are spaces where the overall negative signs are still visible. However, when we move to the Poincare sphere and Bloch sphere, where the overall phases don't matter, there is no difference between a vector's positive version and its negative version. So one rotation in the original space corresponds to 2 rotations on these mathematical spheres, where overall negative signs are ignored. This is the source of the angle doubling relationships between the 2 spaces, and why these 2x1 complex columns are called spinors. Now, we've described the basic mathematics of spinors as 2x1 columns that rotate with SU2 matrices, and don't care about overall phase factors. But it's possible you still find this pretty confusing. So in our next video, we're going to show how we can visualize spinors as flagpoles on a sphere, and show how these spinors are really elements of a space called the complex projective line. This will hopefully make all the mysterious mathematical properties of spinors disappear, and make them seem more like common sense.